Welcome to this explainer. Have you ever actually stopped to think about the completely empty space right in front of your face? I mean, we move through the air around us every single day, and it feels like absolutely nothing. It doesn't drag on our arms, we don't feel a heavy burden on our shoulders. And yet, air is physical matter. It is made of real physical molecules. And because it's matter, it has to have mass, and it must have weight. So today, we're going to explore the fundamental paradox of this invisible ocean we all live in.
Okay, let's dive into this. It's a fantastic question. If it feels weightless, how can it have real weight? Well, we don't feel air simply because our bodies have perfectly adapted to its constant, omnidirectional pressure since the very day we were born. But make no mistake, it is physically pushing on you right now. We're going to systematically solve this central mystery.
Here is our quick roadmap. We'll start with the mystery of air, look into understanding air density, weigh your everyday world, check out the factors that change weight, zoom out to the entire Earth's atmosphere, and finally, hit our key takeaways. Part 1. The mystery of air, and how humanity actually figured it out. For most of human history, treating the background environment as literal nothingness was just the accepted scientific consensus. It's fascinating when you look at the timeline. Back in antiquity, the great Aristotle himself argued that air completely lacked mass. And that view, it stuck around for centuries. It wasn't until the early 1600s that Galileo attempted to directly measure it, though his calculations were off by about a factor of 2. The real turning point happened in the 1640s. A student of Galileo named Evangelista Torricelli inverted a glass tube filled with mercury into a bowl. The mercury fell, leaving a vacuum at the top. Torricelli realized something completely profound. The only thing keeping that heavy liquid pushed up inside the tube was the sheer weight of the invisible air pressing down on the bowl outside it. And this brilliantly illustrates Torricelli's revolutionary shift in human perspective. He famously realized that we do not live in an empty void. He stated that life takes place at the bottom of a sea of air, with real, measurable weight. This single, brilliant experiment led directly to the invention of the barometer, finally giving scientists a way to measure the literal weight of the sky pressing down on us. Part 2. Understanding air density, the absolute foundation of weight. If we actually want to weigh this invisible ocean, we need to understand the foundational math of gases. It all starts with density, which is simply defined as mass per unit volume. The math here is actually incredibly straightforward. To find the weight of the air in a specific space, you just take its density, multiply it by the volume of your container, and factor in gravitational acceleration. But figuring out that initial density value, that requires a bit of standardizing. Now, what's really interesting about this is just how much air density can shift depending on how you measure it. Take the International Standard Atmosphere, or ISA, for example. This is essentially the gold standard for meteorology. At 15 degrees Celsius and standard sea level pressure, dry air has a density of roughly 1.225 kilograms per cubic meter. There are other reference conditions like STP or SATP that give slightly different figures based on varying temperatures and pressures, but for quick mental math, you really just need to remember this. 1 cubic meter of ordinary air at room temperature weighs roughly 1.2 kilograms. Part 3. Weighing your everyday world, from balloons to bedrooms. Let's take that abstract math and apply it to the spaces you interact with every single day. Get ready, because these numbers are genuinely surprising. 108 pounds, or about 49 kilograms. That is the approximate weight of the completely invisible air sitting right now inside a typical 40 cubic meter bedroom.
To put that into perspective, the completely empty-looking space in a standard bedroom contains air that physically weighs more than a large dog. Think about that. You are sleeping in a room filled with a massive, heavy, physical presence that you can't even see.
Let's scale it up and down real quick. A standard 10-liter party balloon, that holds about 12 grams of air. A single-liter bottle of air weighs about 1.2 grams, which is comparable to the physical weight of a small metal paperclip. And if you have an empty one-car garage, say around 50 cubic meters, you are looking at 135 pounds or 61 kilograms of invisible gas trapped inside. As you can see, weight scales directly and linearly with volume. Part 4. Factors that change weight, specifically altitude, temperature, and humidity. In the real world, our environment is dynamic, constantly shifting the weight of the air around us. But before we change the variables, we have to know our baseline. Standard dry air is composed of 78% nitrogen, 21% oxygen, and about 1% argon and other trace gases.
These relatively heavy molecules are what give us our baseline density of roughly 1.2 kilograms per cubic meter. Keep those specific molecules in mind.
Let's move to altitude and see how this builds. Air gets thinner as you go up, simply because there is less air above you pressing down. Pressure and density roughly halve for every 5 to 6 kilometers you climb. In fact, 75% of the atmosphere's entire mass is squished into the bottom 11 kilometers. By the time you get 40 kilometers up, air density is practically zero.
Now, what about temperature? Cooler air naturally contracts and packs its molecules tighter together, keeping density around our normal 1.2 kilograms per cubic meter. But when air is heated, it expands. It spreads out, dropping the density to roughly 0.8 kilograms per cubic meter. This is the exact mechanical principle that allows a hot air balloon to fly. The heat makes the air inside the balloon physically lighter than the cooler air surrounding it, creating buoyant lift.
Finally, humidity. And honestly, this one is deeply counterintuitive. We usually think of a muggy, humid day as feeling really heavy, right? But scientifically, humid air is actually lighter than dry air. Remember those nitrogen and oxygen molecules? They have an average molar mass of about 29 grams per mole. Water vapor molecules, H2O, only have a molar mass of about 18. Because a specific volume of gas at a set temperature and pressure can only hold a fixed number of molecules, the lighter water vapor literally displaces the heavier nitrogen and oxygen. So increasing humidity physically lightens the air.
Part 5. The entire Earth's atmosphere. Zooming out to the macro scale. We've weighed bedrooms and balloons, but now it's time for the grand finale. What happens when we weigh the whole planet's sky? So the crucial point is this staggering number right here, 5.1 times 10 to the 18th power kilograms. That is 5.1 quintillion kilograms. That is the combined weight of every single molecule wrapping our globe. Let that sink in for a second.
5.1 quintillion kilograms sounds unfathomably huge, but on a planetary scale, it's actually remarkably delicate. The atmosphere represents only about 1/millionth of the Earth's total mass. Astronomy textbooks often use a brilliant analogy to explain this. The atmosphere's share of Earth's total mass is proportionally similar to the share of a person's body weight made up by just the hair on their head. It is a massive, heavy ocean to us, but a thin, delicate halo to the planet itself. And all that planetary weight has to go somewhere. Gravity pulls those 5.1 quintillion kilograms straight down toward the surface, which is exactly what creates our atmospheric pressure. At sea level, this results in roughly 1.03 kilograms, pressing down on every single square centimeter of your body. We call this 1 bar of pressure. You don't get crushed because you evolved inside this high-pressure environment, perfectly balanced inside and out. Part 6, Key Takeaways. A quick summary of our journey today. We've covered a lot of ground in this explainer. To summarize, first, we learned what air absolutely has real mass, a fact finally proven by Torricelli in the 1640s. Second, sea level density translates to over 100 pounds of air hiding in an average bedroom. Third, air weight is totally dynamic, decreasing as you rise in altitude, as things heat up, and surprisingly, as humidity increases. And finally, our entire planetary envelope weighs a mind-boggling 5.1 quintillion kilograms. We began with a paradox about how something we move through so effortlessly could actually be heavy matter, and we found that it absolutely is. So, my question to you is this. Knowing you walk through this heavy, invisible ocean every day, a sea of gas that literally weighs more than a large dog in just your bedroom alone, how does it change the way you see the quote-unquote empty space around you? Because the truth is, there really is no empty space. You are swimming at the bottom of an ocean of air. Thanks for exploring with us, and keep questioning the world around you.